Okay, it seems that students are already for that is the end of the class. Well, we still have one topic that we need to cover, although we would not cover it in great details. We would just cover the most essential stuff. And that would be the last topic in the lecture notes set number 4. We would try to do it in a very condensed manner, if you like. Of course, if you want to have a further information, you are always welcome to take a look at the textbook, and then you would have a much detailed information about it. So let me go back to the lecture slide. Well, we have already gone through the first 3 chapters, which are related to some fundamentals of the thermodynamics, first law of thermodynamics, as well as the kinetic theory of gases. In particular, for the kinetic theory of gases, we have introduced the relation between the absolute temperature and the internal energy of an ideal gas, particularly considering monoatomic gases. We have the connection between, for the monoatomic gases, we have the connection between the total internal energy and the absolute temperature. So let me see if I could find the slide which would highlight the equation. For the monoatomic gas, the total translational kinetic energy is equal to 3/2 nRT. And the monoatomic gases can be considered to contain only translational kinetic energy. So that would be a connection between the total internal energy and the absolute temperature of the monoatomic gas. So let me see if it is here. For other gas molecules, such as diatomic gases, the internal energy would be changed due to the consideration of the equipartition theorem. So I try to find out the exact slide which contains the equation. So the internal energy for the monoatomic ideal gas is this one. Is this one? 3/2 nRT. And if you have a thermodynamic process, which is the case of, for example, constant volume process, where the internal energy change is equal to the heat transfer, this would be useful to determine the internal energy change based on a very simple equation that we have learned before, NCV delta T. CV refers to the molar specific heat at the constant volume process, and N refers to the number of moles of gas molecules. And if you have a constant pressure process, on the other hand, then the corresponding molar specific heat has to be changed because work done is involved when you are undergoing a constant pressure process. Remember how you draw the PV diagram? You have a PV diagram. When you have a constant volume process, I to F, the volume does not change. So therefore, the work done, which is the area under the process curve, would be equal to 0. On the other hand, if you have a constant pressure process, there would be an associated area under the process graph. Therefore, there is a work done. And this work done would be provided by the heat energy supplied during the temperature change. So Q refers to the heat transfer, and that would be supplied for both the work done as well as the internal energy change in a constant pressure process. So the value of CV is smaller than CP. For constant volume process, there is no work done. Any temperature change is due to the heat transfer. And in a constant pressure process, like the one shown in the diagram now, you have the temperature change, which involves the internal energy change, and you also involve work done. So heat is used to compensate the two factors, work done as well as the heat, the internal energy change. And for today, we would be going into the second law of the thermodynamics. I have, in the end of the last lesson, show you a video, which is a kind of a 4-minute crash course on the second law of thermodynamics. The fundamental idea of the second law is that there are limitations on the direction of occurrence for a natural process. And the limitation is that some of them can only take place from one direction into another, not the other way around. When you look at the first law of thermodynamics, there is no such a limitation. The first law says, well, always Q plus W equals to delta internal energy change. Nothing is said about the direction. When you have a positive Q, you involve delta E minus W, which is larger than 0. When you reverse the process, it can equally happen by just having a minus value of Q. So there is no limitation whether you have the process comes from the initial point to the final point like here, or the other way around. First law does not say anything about that. But we know for some of the processes, this does not seem to be the case. Say, for the heat transfer, you can always allow the heat transfer from a hot region to a cold region. So if you try to heat up a gas by a flame, so there is a Q, and of course there would be internal energy change and work done. Heating up a gas is easy. On the other hand, cooling the gas does not simply involve taking the gas internal energy and work done, does not simply involve taking away the internal energy and work done. Come on. And put it back into the fire, for example. Common sense tells us that this does not happen. Although first law at here does not say anything why it does not occur. And we are left with the puzzle until we have got the second law. Second law of thermodynamics tells us that, please, don't do silly things. There is, according to our common sense, a certain direction for the process to occur. And to justify the second law, actually, we have to go to more fundamental concept of entropy, which has been introduced in the video. And it is kind of briefly mentioned at the very end of this lecture slide, but we are not going into the detailed calculations. We just take it as a understanding or common knowledge that processes in many cases can only occur in one direction, but not in the other way around, just like the one I have mentioned. And such kind of a concept actually lead to very important consequences. For example, we can never have an engine that has 100% efficiency, not to mention more than 100%. And the reason can be understood by exactly what I have mentioned as a common sense. For example, the heat does not transfer from a cold region to the hot region. So this would lead to a limitation on the efficiency of the heat engine. Now, before we talk about the case of a heat engine, let us think of why we are studying the second law of thermodynamics, or why we are studying the thermodynamics at the beginning. Actually, we actually have to mention about the heat engine. Sorry about that. The idea of the heat engine is, well, we are trying to make use of the heat energy and do some useful stuff, kind of like replacing human labor work with natural energy. And of course, we need to do some engineering in order to make the good use of the natural energy. So people have devised heat engine. Say you are trying to devise an engine like this. You have the ground level, and you have a box that you would like to lift it up to a higher place. How would you do that? Well, old days when we are still wearing skin instead of clothes, we have to use hard work to put the box on our back and then carry it up the cliff, for example. But once we introduce a heat engine, life has changed. Simply, we could put the box on the heat engine, and then we lift it up. When it is at a higher place, we push it to the other side. Well, the work is done, apparently. But think about it. We just talk about one box. What if we have many, many boxes? And of course, you do not have the heat engine that could lift all the boxes all together. So do it one by one. What it means is that your engine, your heat engine, has to return to the original state before it can perform the task once again. That is very important concept. If you have the engine that works only once, who would buy it? Who would use it? Nobody would do that. Nobody would use such a kind of an engine. Right, so with this in mind, everything can be discussed about a heat engine. Say we have this heat engine, and we assume that this is a very simple heat engine that consists of a gas cylinder. And there is a piston. So how does the heat engine work? At the beginning, you have a gas of a certain volume, right? Let me try to draw it on a separate paper. So firstly, you have the heat engine with the piston like that. Then you put the box on top of it. Our task, of course, is trying to lift it up to a higher place. What would you do? You have to cause the expansion of the gas in order to lift up the box to the higher place. How would you do that? Well, various ways for you to do that. You could do work, or you could put in heat energy, causing the expansion of the gas. When the gas expands, it gains internal energy. Temperature rises. So in that way, you would have the extended volume of the gas. The box is here. So you could easily push it to the other side. Now, this is the first part. Then what next? You need to return the piston back to the original point. Now, how would you do that? You need to remove the internal energy of the gas by cooling it down, as well as releasing some of the work done. So in order to cool down a gas, for example, you need to put the gas in contact with a cold region. The cold region may be some cooling water that runs at the surface of the cylinder. Well, just like you put a cloth of that is dipped in the cold water and put it on your forehead, then you feel cold. You take away the heat energy by running cold water around the gas cylinder. So what would happen is the cold water would absorb the heat energy from the gas. And then the gas, of course, would be cooled down, reduced in volume, and returned back to the original state. But there is one catch. When you take away this heat energy from the gas, it is taken away by the cold water. The cold water, of course, gets warm. Can you make use of that heat energy once again? No, because the cold water has to be thrown away. You cannot recollect the heat energy and then put it back into the original gas. You could retrieve a little bit of it, but not all of them. In order to keep the process running, you keep on putting in a lot of heat energy and causing the cylinder to expand. After the cylinder expands, you have to throw away some heat energy to some cool regions. So this heat energy would be lost. You could once again retrieve some of them. For example, the water is a little bit warm, so you could heat up, well, you could heat up some parts of the gas. But if you are having the thermal equilibrium between the cooling water and the gas, then at the end, you cannot retrieve all of the heat energy. You still need to throw away some of them in order to make good use of the energy. So at the end, you would have to throw away some of the heat energy into a cold place. And this is the reason why we would never achieve 100% efficiency. So let us take a look at the physical scenario. When we draw a energy flow diagram of a heat engine. Typically, that is what we would do, like on the top right-hand side. You are having a heat engine, which in the simplest case, it is a cylinder of gas. And in order for it to expand, you need to put in some heat energy. This heat energy would provide the energy for the internal energy change as well as work done. At the end, of course, for the heat engine to work properly, it would be doing some useful work done. It is work done by the heat energy, by the heat engine. But at the same time, the amount of heat energy provided would not be completely used for the work done. Some of them would be used, well, would be thrown away as waste. So this is the wastage, if you like, of the heat energy. So the flow of energy can be summarized by the equation at here. Okay, so is this one? The work by the engine, the work done by the engine, it is equal to heat energy input from the hot reservoir minus the heat energy thrown away to the cold reservoir. And because it is a cyclic process, after one cycle, there would be no internal energy change. So after the cycle, you would expect the system to return to original position. So return to the original state. So there is no internal energy change. All of the work done comes from the net heat transfer. The net heat is the heat energy coming from the hot reservoir minus the heat energy thrown away to the cold reservoir. So the working substance, which in this case is a gas, it absorbs the heat energy from a high temperature energy reservoir. So this is QH. After doing the work, after the engine does the work, the remaining heat energy has to be expelled as heat to a low temperature reservoir. And this part cannot be retrieved back. That is the main message for the heat engine. And from that, we could derive the equation for the thermal efficiency of a heat engine. From the diagram shown in the last page, we could see that all of the input energy comes from QH. Heat energy coming from the hot reservoir into heat engine is QH. And useful output is the work done by the heat engine. Not useful output is the energy thrown away to the cold reservoir, QC. So efficiency of the heat engine. Remember, efficiency is always defined as, in words, useful output over the input required. What is the input in the process? Is QH. What is the useful output? It is the work done by the engine. And if we have the equation work done equals to QH minus QC, then it would be useful to calculate the efficiency by considering either W over QH or 1 minus QC over QH. So that is how we calculate the efficiency. And because we always have to throw away some heat energy, we would not only fail to achieve 100%. In fact, we would never achieve 100% of the efficiency. It is always lower than that. One thing you have to be careful about this equation is the sign of the equation. Now, QH refers to the heat energy input into the engine. Q is positive when heat enters the system. So heat enters the engine, then Q is positive. This means QH should be positive. On the other hand, QC, which refer to the heat energy thrown away by the engine, heat leaves the engine, it should be negative. And numerically, it should be negative because it is the heat thrown away by the engine. So QC, in terms of a value, it should be negative. And that is why we are putting the absolute sign in order to consider just the magnitude at here, in order to just consider the magnitude at this equation. So in any case, the efficiency is the useful work done divided by the necessary input, which useful work done is the input necessary minus the wasted heat energy, QH minus QC. So at here, let's take a look at an example for the calculation of efficiency. You have a heat energy that transfers 2 kilojoule of energy from a hot reservoir and transfers 1.5 kilojoule as an exhaust to a cold reservoir. So how does the efficiency is calculated? How is the efficiency being calculated? Going back to the equation, 1 minus QC over QH. Remember, we just considered the magnitude in this equation for the heat energy. QH is the heat energy input, 2 times 10 to the power 3. QC, heat thrown away as exhaust. So it is 25%. During the process, you have the work done by the engine equals to QH minus QC. So that is how we handle the 3 terms in the calculation. Well, in fact, this question also highlights the even more common scenario of the engine, such as the case of a car. In the case of a car, you burn the petrol and you use it to heat up some cylinders in the engine. The heat energy is provided by the petrol and use it to burn some gas in the cylinder of the engine. At the end, after the car does some work, if you stand at the back of the car, you would fully understand that there must be exhaust heat coming from the car because it comes from the exhaust pipe. The exhaust pipe is always hot. So there must be heat energy lost from the car. And this would be a daily life experience on the efficiency of a car, which is a kind of an engine that is always less than 100%. And the second law of the thermodynamics, in one of the form, it actually states that it is never possible to construct a heat engine which can have an efficiency that is equal to 100%, not to mention over 100%, but it cannot even be equal to 100%. There is always a limit on the efficiency. And 100% is definitely absolute limit in any situation, So this is one form of the second law in the form of a heat engine. It explains the behavior of a heat engine. And actually, when you consider the functioning of the heat engine, it could also be used in other forms. For example, it can be used as a, well, in a reverse way, as a heat pump or as a refrigerator. The idea of the heat pumps or the refrigerator, well, maybe I should not go into the details, but the main idea is we are trying to pump away heat energy from a cold place. We are trying to pump away the heat energy from a cold place. So it sounds like it is against the second law of the thermodynamics, because you never have the flow of the heat energy from a cold place to the hot place. You do not expect the gas cylinder to extract some heat energy and flow it into the fire. That is not possible. However, by engineering, you could actually do it through work done. If you provide some work done, you are actually possible to extract heat energy from a cold place. So you have this QC, which is the heat energy extracted from the cold reservoir. And this has to be done through work into what we call a heat pump. Of course, at the end, this heat pump would gather a lot of energy. It would gather the energy collected from the cold reservoir, and it would collect the energy due to work done. So it would have to throw away the energy to a hot reservoir in this time. So that is TH. Cold and hot is a relative sense. Cold reservoir is at a temperature lower than the hot reservoir. So that is the main idea. Of course, why the heat pump can throw away the energy into the hot reservoir, it is because it is at a temperature higher than the hot reservoir. So that is the idea. If you try to Google, you will find a lot of videos explaining the functioning mechanism of a refrigerator or air conditioner. So in all of those cases, you require an engine. You require an engine to do some work in order to extract the heat energy. Think about it. If you have the old style air conditioner, when you stand at the back of the air conditioner, you could hear the engine starting from time to time because it has to extract the heat energy from the room and throw the heat to the surrounding. Of course, if you are reversing the direction of the refrigerator or the air conditioner, say in the cold places, you could simply reverse the direction of the air conditioner, turn the cold side to the surrounding and turn the hot side to the room. And then you would have effectively a heat pump. So that is how you could make use of the same engine to use it as a refrigerator or a heat pump. And the second law would tell us that you could never have a refrigerator that could simply extract heat energy from the cold reservoir and throw away all of the extracted energy to the hot reservoir without doing any work, without having any work done on the heat pump. This is simply not possible. So that is another format of the second law of thermodynamics. And for the refrigerator or the heat pump, the definition of the performance or efficiency, I would not say it is exactly the same format of efficiency, because if we use the same equation of efficiency, then you would get more than 100%, sometimes in the case of the refrigerator or the heat pump. So in the case of the refrigerator or heat pump, we have another term called the coefficient of performance to define the quality, if you like, the quality of the refrigerator or the heat pump. So always you define the performance, just like the case of the efficiency, by having the useful output that is divided by the input necessary. Going back to the case of the refrigerator, this is how we define the coefficient of performance. The refrigerator, in terms of the function, it is trying to extract heat energy from the cold reservoir, put it into the heat pump with the help of some work. At the end, it will throw away the heat energy to the hot reservoir, which is actually the sum of the work done plus QC. I just try to put absolute sign on both the work done and QC just to make sure that it is the magnitude that is being added. So what is the useful output in this case? Of course, when you talk about a refrigerator, useful output is how much you extract from the cold reservoir, QC. What is the input necessary? It is the work done for the refrigerator. So you could see that this is the different definition compared with the heat engine, but the basic concept is still the same. Useful output on the top, necessary input at the bottom. So a refrigerator can typically achieve a coefficient of performance of 5 and 6, much larger than 100%, of course. So that is not something you would consider comparable between the heat engine and the refrigerator. And similarly, when using the heat pump, the coefficient of performance would be changed accordingly as well. So we are not going once again in the details at here. Right. The problem of not having 100% of the efficiency comes from the fact that many of the processes, they are simply not reversible, or they are just irreversible. Now, a process is fully reversible only when it is in equilibrium. So reversible means that the process can freely go from one direction to the other, or the other way around, without any obstructions. So if you have two parts of the system, one part is ice, one part is water, both at 0 degrees C, then the ice could turn into water and the water could turn into ice at the same rate, and they are in equilibrium. So in that case, the conversion between the ice and the water into ice would be reversible. But on the other hand, if there is a temperature difference, then the transfer of the heat energy between the two systems would not be reversible. It would only take place in one direction. Of course, we could try to make the process that look like reversible by having the process that occurs extremely slowly. For example, you could transfer the heat energy from a hot reservoir to the engine very, very slowly. So this would make the process reversible or close to reversible. How do you do that? Maybe at the beginning, the engine is 20 degrees C. So in order to make the process close to be reversible, you have to first put the hot reservoir at 20.1 degrees C. So there is a very slow transfer heat energy that takes place. Then when the engine becomes 20.1 degrees C, you put it to 20.2. So the process can take place extremely slowly, but it would be close to be reversible. And only when you have a reversible process, then you could have a better chance for the reserving some energy. So I'm not going into details at here. And however, even if you have all processes that are completely reversible, that means you could bring the initial and the final states back to each other without any loss of energy due to irreversible processes. Your efficiency can still be less than 100%. And actually, the highest possible efficiency that can be achieved, for example, for the heat engine, is calculated by means of what we call a Carnot cycle. Now, a Carnot cycle is a special type of a cyclic process. It's a special type of a cycle process, which is operating in an ideal and reversible way between two temperature reservoirs. And the efficiency of the Carnot cycle would set an upper limit on the efficiency of any other engines that is operating between two fixed temperatures. So in order to talk about the Carnot cycle, maybe it's better for somebody else to do it for me, and I would use a YouTube video to show what it is mean by the Carnot cycle.
Good grammar and spelling are important, but if you want to write essays that inspire, messages that forge brighter connections, and emails that get the job done, you need to think about more than just grammar and spelling. This sentence is grammatically correct, but it's wordy and hard to read.
Good day, ladies and gentlemen. Today's topic is the famous Carnot cycle. So what are the things that we need to know about this life-changing cycle? So first, well, it is an ideal heat engine cycle by a French physicist, Sadi Carnot. It utilizes heat energy transferring from a heat source to a heat sink. In addition, it composed of 4 reversible processes. The reversible process means direction can be returned to its original position. Also, it uses ideal gas as its working medium. And note that this is a perfect engine. No friction between piston and cylinder walls, and no heat transfer between the surroundings and your system is considered. Now let's discuss how this interesting cycle works by exploring its processes, the four reversible processes. So now for the first process, process 1 to 2. This process is called isothermal expansion. Isothermal in thermodynamics means no change in temperature, or in other words, temperature is constant or not changing within this process. So what happens here is that the heat energy from the heat source is transferred into the ideal gas. As a result, the gas expands, which then increases the volume and decreasing the pressure. Now next, process 2 to 3, which is called an adiabatic expansion. Adiabatic in thermodynamics means that there is no heat transfer between surroundings and your system, or to put simply, all change in temperature is contained within a system, which as a result making the entropy zero. On this process, our volume increases and pressure decreases. Third process is the isothermal compression. So by compression, it means volume is decreased and as a result, pressure increases. On this process, heat energy from the gas is transferred into the heat sink. And finally, the last process. The last process is called the adiabatic compression. Since it's an adiabatic, all change in temperature is contained within a system, and our entropy is zero. Also, since this is compression, it means our volume decreases while our pressure increases. So that's it. That makes it a cycle. So now let me ask you this. Why Carnot cycle is the most efficient cycle? Mhm. Well, it's because Carnot cycle is a perfect engine. The processes are reversible, working medium is an ideal gas, and of course, the thermal capacity of heat source and heat sink is infinite, which makes no reduction to both during heat transfer, as we have observed, right? But for all those same reasons, it makes this cycle impossible to operate in our real world, as obviously those things don't exist. Well, of course, we should not forget that it contributed so much today. In fact, it is a model of our car engines like Otto and diesel cycle. And so that's it. Once again, this is Easy Engineering. See you again for our other easy and fun engineering topics. Easy engineering topics made easy and fun for you.
Right. Well, the main idea of the video is to show you that how does the Carnot heat engine cycle works out. And the exact reason why we have this Carnot cycle that gives you the best possible efficiency, once again, we have not gone into the details of the, say, the reversible and irreversible processes. So the explanation would require a deep discussion on that topic. And if you are really interested, I would direct you to the textbook for a more detailed reading. At here, we would just take a look at the cycle itself. So the Carnot cycle consists of four processes. So the starting point and the end points are A, B, C, and D. If you have a cycle that runs as an engine, you would be running this cycle in the clockwise direction. You would be running this cycle in the clockwise direction because that would give you a area that is positive, and the work done by the cycle would be negative, and that means the engine would be doing work to the surrounding, and that is exactly what we want. So you have the process, say, that starts from A to B. In this process, you could see that it takes place at a constant temperature TH, which refers to the temperature of hot reservoir, the temperature of the hot reservoir. So the idea is you would inject heat energy to the cycle at a constant temperature process. Now, that sounds a little bit of a joke. So you have the energy of the, you have the temperature of the heat engine, that is TH, and you are trying to inject heat energy at TH as well. So, and you want it to be reversible. How could you do it? So, of course, the idea of a reversible process means that you try to keep the temperature difference between the gas and the reservoir to be as small as possible. When the temperature difference is small, heat transfer takes place over a very, very, very long time. So this would be actually a big problem, as we would mention a little bit later. But in any case, let us assume that it could still take place. Reversible process for constant temperature heat transfer into the engine. Okay, then at the end of the process, at the stage B, it would undergo a diabatic expansion, meaning that there is no heat exchange with the surrounding. And it would be expanding and gets the engine cooled down to a temperature Tc. This Tc would be the temperature of the cold reservoir, where we would lose the heat energy, where we would reject the heat energy to the surrounding. So the process B to C is adiabatic, meaning that there is no heat transfer between the heat engine and the surrounding. All the internal energy change is converted into work done. And then at C to D, there is a constant temperature contraction of the cylinder. So the cylinder loses heat energy to the surrounding at a temperature Tc. It would reject the heat energy. And finally, when it comes to the point D, it will undergo a diabatic process, a diabatic compression back to the point A. So in this way, you have two adiabatic process and two isothermal processes as labeled as A, B, C, and D. So for this cycle, the relation between QH and QC, we do not derive it at here, but the relation between QH and QC is actually very, very simple. QH and QC, they are actually related to the absolute temperature of the hot and cold reservoirs. Basically, QC over QH is equal to TC over TH for the Carnot cycle. So if you are running a Carnot cycle as a heat engine, then the efficiency of this Carnot heat engine is equal to W divided by QH, or 1 minus QH over QC. Using the relation at here tells you the efficiency of a Carnot cycle is equal to 1 minus TC over TH. Of course, T is in absolute temperature scale, and so its unit is Kelvin. This would set the actual limit of the heat engine efficiency provided with the temperature of the hot and cold reservoirs. Provided with the temperature of the hot reservoir being TH and temperature of the cold reservoir being TC, maximum possible efficiency that you could achieve theoretically is given by the Carnot cycle. And the efficiency is 1 minus TC over TH. Any real engines would have efficiency lower than this value. So does it mean that we could run the heat engine using a Carnot cycle? The answer is no. As explained in the video, you need to have reversible processes for the Carnot cycle. And for example, in the isothermal heat transfer processes, how could you transfer heat energy in a reversible way? You have very small temperature difference, and that means infinitely long time. So you could achieve high efficiency at the expense of the time. According to the engineers, that is simply not possible. You cannot let the car run one cycle over 10 years. You cannot let the car run for 10 meters over a very long period of time because it takes a long time to finish one cycle. So that is not practical at all. But here, the Carnot cycle gives you the theoretical limit on the efficiency. And of course, if TH is equal to TC, because it is a heat engine, you would expect zero efficiency. And only when you have TC equals to 0, then you have 100% efficiency. But TC equals to 0 does not exist because you could never achieve an environment that is exactly equal to 0 Kelvin. So how do you achieve a high efficiency in general? From the Carnot cycle efficiency, we could say that in order to achieve a high efficiency, what we could do, raise TH, raise the temperature of the hot reservoir. And that is basically the only way you could achieve a higher efficiency for any heat engine, Okay, at here, let's take a look at a example. In this example, you have a heat engine, actually a steam engine. And heat energy is provided by a hot reservoir, 500 K. The engine, the energy from the burning fuel heats up the water and drives a piston. The waste heat energy has to be lost to the surrounding air at 300 K room temperature, basically. So what would be the maximum possible efficiency? By the Carnot heat engine cycle, the maximum efficiency we could get for the Carnot cycle, it is defined as this, 1 minus TC over TH. So maximum possible efficiency is 40%, which is limited by the reservoir temperatures, limited by the temperature of the cold reservoir and the temperature of the hot reservoir. So if we want to raise the efficiency, what could we do? We could raise the temperature of the steam. So raise the temperature of the hot reservoir or lower the temperature of the cold reservoir. For example, we cool the gas, cool the steam at cold water or even ice, if you like. So the idea is demonstrated in the second part of the question in the example. When you lower the temperature of the cold reservoir or raising the temperature of the hot reservoir, what we would get? Well, efficiency, of course, can be increased in both cases, but practical, whether the situation is practical or not, it depends on highly the scenario. Cooling the reservoir down to 250 K, which is minus 27 degrees C, does not seem to be very practical in many situations. And here we also briefly mention the Carnot cycles as operating in the refrigerator mode or in the heat pump mode. So this is just mentioned here for your reference, and we will not put it in the test in the examination. So we will just mention it briefly at here. Once again, the idea is whenever you are running the Carnot cycle, QC over QH is equal to TC over TH. So in the heating mode, that means you are working the Carnot cycle as a heat pump. The work done is equal to QC minus QH, QH minus QC. QH minus QC. So that is why you have the coefficient of performance in a heating mode for a Carnot cycle, then it is TH over TH minus TC. And in the refrigerator mode, it will be TC over TH minus TC, based on the fact that in the Carnot cycle, QH over QC is equal to well, QC over QH is equal to TC over TH, as I just has highlighted. Right, I should not go into the topic of entropy because that is something completely new, and introducing this concept would just be more tedious in the explanation. In any case, the textbook would be available for any students who are curious about the topic. And I believe that for the at least mechanical engineers in this class, you would be seeing this topic a lot in the second year of your studies. So at here, the main message is how do we define the efficiency of a heat engine, and what is the maximum possible efficiency we could get from any heat engine, and that is limited by the efficiency of a Carnot cycle. So efficiency of a Carnot cycle is defined in this equation. Okay. Right. At here, we would be finishing the whole course of Physics 1. So we start from the mechanics, and then we've gone through the waves, and finally, we have learned about the thermodynamics. So it has been a long journey. And remember that in your examination, all the topics will be covered, that all the topics that we taught would be covered. So let me see if I could log in. Maybe I could log in from another computer. Right, just a minute. Okay. So all the materials, they should be available on the lecture slides, of course. remember there would be still assignments that you have to finish. There would be still assignments that you have to finish. The last assignments would be assignment 4.3. There would be no assignment 4.4. I would just post it here for your reference for the assignment 4.4. And the materials that you should know would be all available on the lecture notes. Remember, next Tuesday, we would be having a rehearsal session for the online invigilator examination. Please log in at around 9:15 in the morning, 9:15 Hong Kong time in the morning. So we would be having a rehearsal session around 1.5 hours. The idea is mainly for us to help you to understand how the online examination works. A number of things we would do in particular. First, we would check whether you have submitted your identity document. If you still have not done so, please do it as soon as possible. Follow the instructions on the student guide and submit us the document. And secondly, you should be doing a mock exam. Wow, this mock exam is not asking you to write down answers of questions. Rather than that, we are asking you to take picture of something, save it as a PDF file, and then submit it to Blackboard, just as the real examination. So in the rehearsal session, we would check your setup. If your setup is not up to the standard, we will tell you what is not up to standard. In case you are in Hong Kong, if you really cannot meet the requirement, you may request for coming back to campus and use the network on campus to do the online invigilator exam. You would have until next Tuesday to submit the application. Right. So one of the students is asking question. You would know the results on the 9th of December because we have to pass all your applications to AR for approval. They may not have sufficient space for all the students. They may not have sufficient space for all the students. In particular, these days, you do not want too many students in one room. So we cannot guarantee anything. But remember, if you are coming back to campus for the exam, you still need to have devices ready. Say the computer to log in the Blackboard, the device for Zoom, and also the device for taking the pictures of the exam paper. So that is something you should bear in mind, even when you go back to campus. If you don't want to come to campus for exam, you just forget about it. We would not take care of it at all if you do not write anything. So that is okay. Right. So I guess it would be good if you could type the message for all the people so other students could benefit. If you have doubt on the Wi-Fi in your PolyU residence hall, well, you could also apply for coming back to the campus. You could also apply for coming back to campus. Carnot cycle would be covered, and coefficient of performance would not be covered, but Carnot cycle would be covered. Okay, I would stop the video at here first.